In this module, we will discuss the pre-equilibrium approximation. In the previous modules devoted to complex reactions, we have encountered that as the complexity of reaction mechanisms increases, so does the mathematical complexity of solving the corresponding differential equations and obtaining integrated rate laws. This is particularly noticeable when dealing with mechanisms involving second and higher reaction orders, multiple steps, or reversible reactions. This mathematical complexity quickly escalates to a point where analytical solutions become nearly unfeasible. One way to handle complex reaction schemes is to perform numerical integration of differential rate laws. This is a valid approach, but it rather belongs to the field of mathematics and informatics and beyond the scope of this course. To address the challenge of complex reaction mechanisms, we often resort to kinetic approximation methods. The main idea of these methods is to simplify equations describing reaction mechanisms based on underlying physical properties of studied systems. This strategy distinguishes them from mathematics-based methods mentioned before. Two such kinetic approaches are the pre-equilibrium approximation and the steady-state approximation. These approximation methods are able to yield more manageable expressions and interpretable results for complicated reaction mechanisms, making them more accessible for study and application. The pre-equilibrium approximation is applied when an intermediate is in equilibrium with the reactants. It assumes that certain steps in a reaction mechanism reach equilibrium rapidly compared to the subsequent steps leading to product formation. This approach simplifies the analysis by allowing us to treat these early reaction steps as if they were at equilibrium, simplifying the evaluation of the overall reaction mechanism. Consider a reaction mechanism where an intermediate C reaches equilibrium with reactants A and B before a further reaction. It is depicted in the following reaction scheme. In this mechanism, the reversible reaction 1 links the intermediate C with the reactants A and B. The decay of C in the irreversible reaction 2 leads to the formation of the product D. The pre-equilibrium approximation applies when the elementary reactions of the reversible reaction 1 are much faster than the decay of the intermediate to form the product. Under these conditions, the reaction can be conceptualized as occurring in two distinct phases. Initially, an equilibrium is quickly established between the reactants and the intermediate. This equilibrium is maintained throughout the course of the reaction. Subsequently, the intermediate decays to form the product. The pre-equilibrium approximation simplifies the analysis of the reaction mechanism by focusing on the slower rate-determining steps. To apply the pre-equilibrium approximation, consider the following differential rate expression for the formation of product D. D concentration of D by dt equals to K2 times the concentration of C. In this equation, the concentration of species C can be expressed in terms of the concentration of reactants A and B, assuming that C is in equilibrium with these reactants. This leads to the following relationship. The concentration of C equals Kc times the concentration of A times the concentration of B. Here, Kc represents the equilibrium constant of the reversible reaction 1, defined as the ratio of the forward and backward rate constants. Substituting this expression into the differential rate equation for D, we obtain this expression for the rate of product formation. D concentration of D by dt equals effective rate constant multiplied by the concentration of A multiplied by the concentration of B. This equation demonstrates that under the pre-equilibrium approximation, the rate law for the formation of D is first order with respect to both reactants A and B and second order overall. This composite rate constant effectively combines the kinetics of the fast reversible reaction 1 with the slower elementary reaction of product formation 2. In analyzing the temperature dependence of reaction rates, particularly in the context of the pre-equilibrium approximation, it is necessary to recognize that the effective rate constant, Kf, may not always increase with temperature. This is because Kf depends on three individual rate constants, which themselves have distinct temperature dependencies. If the rate constant for the reverse reaction, K-1, increases with temperature more rapidly than the product of the forward rate constants, K1 and K2, then Kf will decrease as temperature increases. This scenario leads to the unusual situation where the rate constant of the overall reaction, Kf, formally has a negative activation energy. To understand this better, consider the Arrhenius temperature dependence for each rate constant. Here, EA1, EA2, and EA-1 are the activation energies for the forward and reverse elementary reactions respectively. The effective activation energy of the overall reaction is then the activation energy of the elementary reaction 1 plus the activation energy of the elementary reaction 2 minus the activation energy of the elementary reaction minus 1. This effective activation energy is positive if the sum of the activation energies for the forward reactions exceeds that of the reverse reaction. Conversely, it is negative if the activation energy of the reverse reaction is greater than the sum of the activation energies for the forward reactions. This highlights the need for caution when predicting the effects of temperature on complex reactions that proceed through multiple elementary steps, as the overall reaction kinetics can be counterintuitive. The reaction between nitric oxide and oxygen to form nitrogen dioxide serves as an illustrative example of the application of the pre-equilibrium approximation in understanding reaction mechanisms. The experimental rate law for this reaction is second order in NO and first order in O2. Initially, one might consider a reaction mechanism of a single trimolecular elementary reaction between two NO molecules and one O2 molecule. However, as temperature increases, the reaction rate unexpectedly decreases. The experimental temperature dependence of the reaction rate contradicts this mechanism consisting of one elementary reaction. The proposed alternative reaction mechanism involves two steps: a rapid equilibrium between NO and its dimer N2O2, A slower bimolecular reaction between N2O2 and O2 to produce NO2. In the first step, the equilibrium in a reversible reaction between NO and N2O2 is established quickly compared to the rate of NO2 formation. Applying the pre-equilibrium approximation to the first step, the concentration of N2O2 is expressed as Kc times the concentration of NO squared. The reaction rate for product formation in the second step is K2 times the concentration of N2O2 times the concentration of O2. Substituting the expression for the concentration of N2O2 into the rate equation, we get the reaction rate equal to the product of the effective rate constant, the concentration of NO squared, and the concentration of O2. This rate law is consistent with the experimental reaction orders, second order in NO and first order in O2. Moreover, the reaction mechanism involving a pre-equilibrium explains the observed temperature dependence. The formation of N2O2 is exothermic, so an increase in temperature shifts the equilibrium towards NO, reducing the amount of N2O2 available to react with O2. Consequently, the rate of NO2 formation decreases with an increase in temperature. This analysis not only aligns with experimental observations but also provides deeper insight into the reaction mechanism.